So we'll talk about something very different today, very different to my normal image filtering sort of videos. That is buffer overflow exploits and what they are and how you do them, which is kind of fun. I'm, obviously somewhat of a geek. I quite like these sort of things, low-level memory exploits. A buffer overflow exploit is a situation where we're using probably a low-level C function or something to write a string or some other variable into a piece of memory that is only a certain length. But we're trying to write something in that's longer than that, and it then overwrites the later memory addresses, and that can cause all kinds of problems. The first thing we should talk about probably is roughly what happens in memory with a program when it's run. Now we're talking about C programs in Linux today, just because I happen to have a Linux VM running here, and it's easier. But this will apply to many different languages, many different operating systems. So when a program is run by the operating system, so we're in some shell and we type in a command line to run a program, the operating system will effectively call as a function the main method of your code. But your actual process, your executable, will be held in memory in a very specific way. And it's consistent between different processes. So we have a big block of RAM. We don't know how big our RAM is because it can be varied, but we use something called virtual memory address translation to say that everything in here, this is 0, OX 0, 0, 0, ... This is the bottom of the memory, as it were. And up here is OX F, F, F. So this is the equivalent of 11111111 memory address all the way up to 32 or 64 bits. And this is 0. Now, when you use this, there are certain areas of this memory that are always allocated to certain things. So up here, we have kernel things. So this will be command line parameters that we've passed to our program, and environment variables and so on. Down here, we have something called the text. That's the actual code of our program. The machine instructions that we've compiled get loaded in there. Now that's read-only because we don't want to be messing about down there. In here, we have data. So uninitialized and initialized variables get held here. And then we have the heap. Now, the heap may have been mentioned from time to time. It's where you allocate large things in your memory. Big area of memory that you can allocate huge chunks on to do various things. Okay, what you do with that is of course up to your program. And then up here, perhaps the most important bit, in some ways anyway, is the stack. Now the stack holds the local variables for each of your functions. And when you call a new function, like let's say you say printf and then some parameters, that gets put on the end of the stack. So the heap grows in this direction as you add memory, and the stack grows in this direction. Now that I've laid that out, we won't talk about it anymore. We'll just focus on the stack, okay? Because that's where a lot of these buffer overflows happen. You can have overflows in other areas, but we're not going to be dealing with them today. I'm going to turn this sideways because I think it's just a little bit easier to understand. At least that's how I tended to look at it. Okay, so this is our memory again, nice and big. This is now our stack area. Excuse my programmer's writing. Up here we have the high memory addresses, ff ... So something up here is high, and this is OX 0, 0, 0. Now, of course, the stack won't be taking up this whole region, but it doesn't matter. So high memory addresses and low memory addresses. And the stack grows downwards. So when we add something onto the end of a stack, it gets put on this side and then this moves in this direction. Of course, I'm talking about a stack without telling you what a stack is. Professor Brailsford's already talked about this and probably done a much better job of explaining it than I would.
There's a lot of computer science depends on stacks. I sometimes think that stacks and trees is just about all computer science is about.
So we'll just say that you know how a stack works and then we'll move on. We have some program that's calling a function. A function is some area of code that does something and then returns back to where it was before. So this is our calling function here. When the calling function wants to make use of something, it adds its parameters that it's passing onto the stack. So this will be parameter A and this will be parameter B, and they will be added into the stack in reverse order. And then the assembler code for this function will make something called a call, and that will jump to somewhere else in memory and work with these two things. And it's the nature of this stack that causes us to have problems. Let's look at some code and then we'll see how it works. I've got myself here a program that isn't very good. I wrote it. So it's a piece of C code, so if we look at it, it's just a very simple C code that allocates some memory on the stack and then copies a string into it from the command line. Okay? So up here, we've got the main function for C that takes the number of parameters it's been given and then a pointer to those variables that you've got. And they'll be held in the kernel area of our memory. We allocate a buffer that's 500 characters long, and then we call a function called string copy, which will copy our command line parameter from argv into our buffer. Our function puts on a return address, which is the place in the code that we need to go back to once we've done the string copy. So that's how main knows where to go after it's finished. And then we put on a reference to the base pointer in our previous function. We won't worry about that too much because it's not relevant particularly to this video. So this is just going to be our EBP base pointer. This is our allocated space for our buffer, and it's 500 long. If we write into it something that's longer than 500, we're going to go straight past the buffer, over this, and crucially over our return variable. And that's where we point back to something we shouldn't be doing. Okay? So what I'm going to do is walk through it in the code, and then let's see if it works. So this is my Kali Linux distribution, which has all kinds of slightly dubious password cracking tools and other penetration testing tools. It's meant for ethical hacking, let's just make that clear. I've written here a small function that does our copy from the command line. Okay, now I've compiled it and I can run it. So I can run my vulnerable code with hello, and that will copy hello into this buffer and then simply return. So nothing happens. It's the most boring program ever.
Another program might do something like copy hello in there, and then now it's in the buffer, they can go off and process it.
Yeah, I mean, maybe you've got a function that makes things all uppercase. So you copy hello off, then you change this new copy to be all uppercase, and then you output it to the screen. And this doesn't have to be main, this could be any function. We're going to run something called GDB, which is the Linux command line debugger. I wouldn't advise using GDB unless you really like seeing a lot of assembly and really doing low-level Linux things.
There's a lot of text on the screen there, so we don't have to worry about
No, this text here is just warranty information.
Oh.
So now I'm going to type in list, and it shows us the code for our function. So we can see it's just a compiled function. Now it knows this because the compiler included this information along with the executable. Now we can also show the machine code for this. So we can say disassemble main, and we can see the code for main.
So they're the instructions that would actually go to the CPU?
These are the actual CPU instructions that will be run, okay? Now, we won't dwell on much of this because assembly is perhaps a whole series of talks by someone other than me. Steve Bagley knows a lot about assembler. However, a couple of really important things are, this line here, sub of OX1F4 from ESP, that's allocating the 500 for the buffer. That is, we're here and we go 500 in this direction, and that's where our buffer goes. So buffer's sitting to the left on this image, but lower in memory than the rest of our variables. Okay. Now, we can run this program from GDB, and if it crashes, then we can look at the registers and find out what's happened. So we can say run hello, and it will start the program and say hello, okay? And it's exited normally. Now, we can pass something a little bit longer than hello. If we pass something that's over 500, then this buffer will go over this base pointer and this return value and break the code.
So that'll just crash your...
It should just crash it. Python, for example, can produce strings based on simple scripts on the command line. So what we do is we say run, and then we pass it a Python script of print 41, that's the A character, 500 and let's say 6 times, okay? Just a little bit more than 500, so it's going to cause somewhat of a problem, but not a catastrophe, okay? And then we run that, and it's received a segmentation fault. Now, a segmentation fault is what a CPU will send back to you when you're trying to access something in memory you shouldn't be doing.
Right.
Okay? Now, that's not actually happened because we overwrote somewhere we shouldn't. What's happened is that the return address was half overwritten with these 41s.
So it doesn't know what it is.
So yeah, there is nothing in memory at B7004141. And if there is, it doesn't belong to this process. It's not allowed, so it gets a segmentation fault. So if we change this to 508, we're going 2 bytes further along, which means we're now overwriting the entire of our return address. We're overwriting this ret here with 41s. Right. Now, if there was some virus code at 41, 41, 41, that's a big problem. Okay, so that's where we're going with this. All right, so we run this, and you can see the return address is now 41, 41, 41, 41. Now I can show you the registers, and you can see that the instruction pointer is now pointing at 41, 41. So that means that it's read this return value and tried to return to that place in the code and run it. And of course it can't. Now we can have a little bit more fun, okay? We've broken our code. What can we do now? Well, what we need to do is change this return value to somewhere where we've got some payload that we're trying to produce, okay? So luckily, if I quit this debugger, I have some pre-prepared payload just for this occasion, okay? Now, in fact, this payload is just a simple, very short program in assembler that puts some variables on the stack and then executes a system call to tell it to run a shell, okay, to run a new command line, okay? So if I show this code, shell code, okay, This code will depend on the Linux operating system and on whether you're using an Intel CPU or something else. Okay, this is just a string of different commands. Crucially, this xcd x80 is throwing a system interrupt, which means that it's going to run the system call. Okay, that's all we'll go into about this. What this will actually do is run something called ZSH, which is an old shell which doesn't have a lot of protections involved. So let's go back to our debugger, and we're going to run again, but this time we're going to run a slightly more malicious piece of code. We're going to put in our 41s times by 508, and then we're going to put in our shell code. There we go, okay? So now we're doing all 41s and then a bunch of malicious code. Okay? Now that's actually now too long, we've gone too far, but we'll fix that in a minute. Okay? And finally, the last thing we want to add in is our return address, which we'll customize in a moment. To craft an exploit from this, what we need to do is remember the fact that string copy is going to copy into our buffer. Okay? So we're going to start here. We want to overwrite the memory of this return address with somewhere pointing to our malicious code. Okay? Now, we can't necessarily know for sure where our malicious code might be stored elsewhere on the disk, so we don't worry about that or on memory. We want to put it in this buffer. So we're going to put some malicious code in here, and then we're going to have a return address that points back into it. Okay? Now, memory moves around slightly. When you run these programs, that things change slightly, environment variables are added and removed, things move around. So we want to try and hedge our bets and get the rough area that this will go in. In here, we put in something called a no-op sled, or there's various other words for it. So this is simply /x90. That is the machine instruction for just move to the next one. So that's good. Anywhere we land in that no-op is going to tick along to our malicious code. So we have a load of x90s here. Then we have our shell code, right? That's our malicious payload that runs our shell. And then we have the return address right in the right place. We have our return address that points back right smack in the middle of these x90s. And what that means is even if these move a bit, it'll still work.
So it's like having a slope almost, is it?
It's exactly like that, yes. Anywhere we land in here is going to cause a real problem.
So we've got our bomb or our, I don't know, pit of lava.
Yeah, it's the Sarlacc pit, isn't it, right? And your no-op sled takes you in and then you get digested over 10,000 years or whatever it is. So we've got three things we need to do. We need to put in some x90s, we need to put in our shell code, which I've already got, and we need to put in our return address. We'll worry about the return address last, okay? So if we go back to my code, we change the first x41s that we're putting in, okay, we change to 90. So we're putting in a load of no-op operations. Then we've got our shell code, and then we've got what will eventually be our return address. And we'll put in 10 of those because it's just to have a little bit of padding between our shell code and our stack that's moving about. Now, this 508 here, people will have noticed now this is too big because we're putting in extra information. So if we write 508 bytes, it goes exactly where we want over our return address. But we've now got 43 bytes of shell code and we've got 40 bytes of return address. So minus 40, minus 43 is 425. We change this 508 to 425. And so now, this exploit here that we're looking at is exactly what I hoped it would be here. Okay, some x90, no operation sleds, the shell code, and then we've got our return address, which is 10 times 4 bytes. We run this, and we've got a segmentation fault, which is exactly what we hoped we'd get, because our return address hasn't been changed yet. So now let's look at our memory and work out where our return address should go. So in GDB, it's paused the program after the segmentation fault. So we can say list the registers at about, let's say 200 of them, at the stack pointer minus 550, okay? So that's going to be right at the beginning of our buffer. And what we're seeing here is a load of 90s in a row, okay? So we just need to pick a memory address right in the middle of them. So let's pick this one, let's say B, FF, FF, ABA, okay? I'm going to write that down so I don't forget it, okay? Now, there's a nice quirk in this, which is that Intel CPUs are little endian, which means I have to put it in backwards. But it's, yet more things we have to learn, but it's fine. BF, FF, FA, put caps lock on, and can't type when people are watching, and BA, okay? Now, theoretically, when I run this, what will happen is string copy will do its thing. It will copy its string in, and then when it tries to return, it will load this return value and execute that instruction, which will be somewhere in this buffer, and then it will read off and run our shell code. So we should get a shell, okay? And we did. Okay? So that's a good start, right? We know our program works, albeit in a debugger with very little side effect, okay? The question now is, can I take this and use it on the command line to gain access to this machine? Now, Linux has quite restrictive policies on what can and can't be done from certain programs. But some programs, such as changing your password, are run using something called SUID. So what that means is that for the sake of running that program, you are a complete root, you have root access to that machine, because otherwise how could you change the password file? You're not normally allowed to even read it, the shadow file. So if you find a vulnerability in that kind of program, and there's more than I think there should be, then that's when there's a real problem. Now obviously these vulnerabilities are getting rarer, but it's catastrophic if you get one. Okay, so let's leave this debugger, okay, and then back to our nice clear command line environment. Okay, so if I list the files we've got, this vulnerable program here is shown in red. That shows that it's SUID root, okay, which means when we run it, it will be running as root, which is not great for security. Now, that and my shoddy programming, which means it's vulnerable to a buffer overflow. Okay, so if I copy my exploit, okay, here we go. So this is the big moment of truth, right? Whether this whole video is going to work. I've put my code in, okay? This is just like it was in the debugger, okay? I've tried to make it exactly the same so that the memory doesn't move around. Let's just say, who am I on Linux? So we can say, I am myself, okay? I don't have root access. So can I, for example, look at the password file? So I can say cat, etc/shadow. Permission denied, no dice, okay? Fair enough, I'm not supposed to be looking at that. Now I run my exploit. So mexec, my vulnerability with the right address, and we've got a shell. Who am I? Root. Okay, so now can I look at my shadow file?
So root is like God for this system.
In Linux, there is nothing you can't do with root. Okay, so I've got my root shell and I'm root, so I can cat/etc/shadow, and I can see what's in the shadow file. But the point is that there's nothing I can't do now. I can wipe the machine or do anything like that myself. And then I can quit this, and then my program just gracefully exits because it now returns to normal code, and hopefully no one is any the wiser that anything's gone on. Now, there are things that the operating system does to try and stop this from happening. Randomizing your address, your memory layout, and things like no executing of stacks and stuff. There are ways around this. They're obviously for a different video. But at least things are getting definitely better.
Stealth and botnets usually go hand in hand because from the point of view of a CNC server, it wants to ensure...
And some years ago, it seems the NSA got a backdoor in one of these routers, presumably because they got one of their people to get a job.